Welcome to my channel. If you like my videos, then kindly subscribe, like and watch. Thank you.
Bismillah Rahman Rahim. Welcome back. Chapter number 10, that is about column. So before starting this lecture, let me tell you that you can also find my lectures on this website that is created by me. I will give you an overview. You can see the solve problems that are available in this website. You can easily watch them and you can learn them. So all the problems are also available over here. So if you are interested in lecture videos, you can also find organized lectures and in sequence. So you can also find them on this website here. If you are interested in playlist of, so you can also go to this website in order to check the videos. Okay, now let's move toward our main topic, that is about column. So in this chapter we are going to study the stability of structure. First we will define the behavior of column in terms of stability. Then we will develop Euler's formula for pin-ended beams, its effective length to account for different end condition, that will be covered in extension of Euler formula for other type of end conditions. And we will discuss sample problem, then eccentric loading, secant formula for analysis of eccentrically loaded columns, and then you will be able to design of column under centric load and design of column under eccentric load. So this lectures will be this lecture will be all about the columns. Okay, so before starting column or this lecture, let me explain what is column. So column is a structural member. It can be either horizontal or it can be a vertical, but mostly they are vertical member. So let's say this is the axis of this member and this is the axis of this member. So columns may be defined as the structural member which carry the axial loading. So this is axis and the load is applied like this, or this is the vertical member and that is exerted upon by a axial load. Clear? So they are known as column. I will repeat, the column are structural member which carries the axial loading. So here you can see this is the member which carries axial load, so this is known as column. And in axial loading it is compressive, it supports the compressive stress or force, while here it is also a column because it carries or it supports the axial loading. While beams are defined as the members which carry the transverse loading. By transverse loading we means the load that is perpendicular to the axis of beam. So for example, if this is the beam, clear, and there is a loading, so you can see that this load is perpendicular to this axis. This is transverse loading. Clear? Transverse loading. So this is known as, this structural member is known as beam because it carries the transverse loading. Or beam may also be defined as a structural member which supports bending moment, because due to this load there will be a bending moment. So beam may be defined as the structural member which carry the which supports the bending moment, or in which the load is perpendicular to the transverse. The load is perpendicular to the axis. They are called beam. So this is the example of beam. You can also take the example of beam like that. This is a structural member, clear, and there is a, this is the axis of the beam, clear, and the load is acting like this, P, clear. So here you can see this load is perpendicular to this axis, and that is why this is known as transverse loading, and this beam is this structural member is also known as beam. So from this definition, now it is clear to you what is difference between column and beam. So column carries the only axial compressive load, while beam carries the transverse loading. And for example, if a beam that carries both the axial load as well as transverse load, for example, this is axial load and this is transverse load, clear. So these are known as beam column, beam column. So we cannot define the column as vertical members only. This is the confusion mostly found in students, that they consider that vertical members are known as column while horizontal members are known as beam. So they are only defined by the type of loading they are carrying. So they are independent of this definition is independent of the orientation of column. Column carries the axial loading, clear, while beams carries the transverse loading. Okay, so until now we have discussed in our previous lectures that in our previous lectures we discussed the two primary concerns. The first one is about the strength of material, and the second one is elongation. So by strength of material, we means that the ability of any member to support a specified load without experience excessive stress. So without exceeding specific stress, the material can bear the load. So that is defined as strength of material, while elongation means the ability of structure to support a specific load without undergoing unacceptable deformation. So here this deformation should be maximum deformation, and it should be less than the allowable deformation, clear. So this chapter is concerned with the stability of structure, or mainly stability of column. So by stability we mean that the ability of a structure to support a given load without experiencing a sudden change in configuration. So we will discuss this stability in our next slide. So you can see the stability of structure. You can see this is a column AB of length L that is pin supported at both ends, clear, and that is acted upon by a centric axial load. By centric axial load means that it is passing through the center of this column, clear. So if this load is applied on this column, so definitely due to this load the stress will be there, and that stress will be equal to P by A, where A is the cross sectional of area of the column. For example, if this is the column here, so due to this load P acting over this area A, so this stress will be equal to P by A. So if A is the cross sectional area that is selected, so the value of stress will be P by A on the transverse section. Why transverse section? Because this is the axis, so this area is perpendicular to this axis. So this is a transverse section, and this stress should be less than the allowable stress for safer design for the material that is used. Also, due to this load P, there will be deformation, and we have studied in our previous lecture that this deformation is equal to PL divided by AE, and also this deformation should be less than the allowable deformation or the deformation that is specified in the problems or by the designer. So if both the conditions are satisfied, so we consider that the design is okay, or we can say that the column has been properly designed. However, you can find that as this load is applied on the beam, the column may buckle like this, that is shown in the figure. So it may bend like a sharp curve. So this phenomena is known as buckling. So instead of remaining straight, it suddenly become a sharp curve as shown over in this picture. Clear? So clearly a column that buckle under the loading is to be support is not properly designed. So what we have to understand, we have to check the stability of structure. So how can we check the stability of structure? So if we want to get into the actual discussion of the stability of structure, we will discuss some problem by considering the simplified model consists of two rigid rods. So here you can see this is the main model of the columns. You can see the two rods, rigid rods AC and BE, that is pin connected at point C, and there is a torsional spring having constant K. The length of this rod or column is L by 2, and length of this CB is L by 2, that is acted upon by a load P. And there is a torsional spring at point C of constant K. So if I draw the free body diagram of this model of columns made up of two rigid rods joined by a torsional spring, so it will be like this. This is rod AC, and this will be rod BC. Clear? So here there will be a torsional spring K, and the load is P and P dash. Clear? If the two rods and force P and P dash are perfectly in line, if these two forces are perfectly aligned and these two rods are perfectly aligned, so the system will remain in the position of equilibrium as shown over here. Clear? But if you disturb it at point C, this is point C, this is point A, and this is point B. So if you disturb it at point C, or if you move this point C to the right side as shown in the figure. Clear? So there will be each rod will form a small angle delta theta with this vertical axis. So initially it was straight. Clear? So if you move this, so the rod will bend like the deflect like this. Clear? And it will be acting like this. So if this is the initial, so this is the angle, that is delta T, and this angle is very small, that is shown over here. Clear? Similarly, in below rod there will be angle theta, del theta will be there. Okay. So what will happen? Will the system will return to the original position or not? To answer this question, we take this rod AC that is separately shown in figure. So if you want to analyze this rod AC, so definitely there is a force P acting, and if you want to move this force to this point P and you want to remove, so there will be a reaction moment as well. Clear? Now you can see that due to this force and this force there will be a couple, because the perpendicular distance is this one. Clear? And this distance is represented as, this is the distance, and this distance is represented as sine. If you take the sine of this delta t, so it will be equal to this distance divided by the hypotenuse, which is equal to, let this distance is let any value, that is x. Clear? So this will be x by L by 2. Clear? So this x distance will be equal to L by 2 sine of delta theta. So this perpendicular distance is L by 2 sine of theta. So due to this force into perpendicular distance, there will be a couple, and that a couple or moment, and that moment is equal to P into perpendicular distance is L by 2 sine of delta theta. Clear? And this movement is known as distorting movement. I will represent is MD. MD is equal to distorting movement. It will tend to distort the system. Clear? Now we have already told you that there is a torsional spring at the point C. So due to this torsional spring there will be a moment, and that moment will be equal to K into 2 delta theta. Why 2 delta theta? Because you can see here this point C moves toward this point. Clear? So this angle with the axis of this center, it will be 2 theta. This is theta and this is theta. So total is 2 del theta. So this due to this torsional spring, the moment will be K into 2 delta theta, and this moment is known as restoring moment. Why? Because this torsional moment tend to restore the system to its original position. So this MR is restoring moment. Okay. Now if your MD is greater than MR, clear? So distorting movement is greater than restoring movement. So definitely a system will be unstable. It will not go back to the original position. So if your restoring movement is greater than the distorting movement, so definitely it will be stable and it will bring the system to the original position. Now for finding the load at which the system will be able to bring back to the original system, so this distorting moment is equal to the restoring moment, and this MD is equal to P into L over 2 sine of theta is equal to K into 2 del theta. Now we have considered this del theta is very small angle. So if del theta is very small, so sine of this is del theta. Sine of del theta will be approximately equal to del theta. So you can put the del theta over here. I will write over here. So it will be equal to P into L by 2 into del theta is equal to K into 2 del theta. Del theta will cancel with this, and we will have P is equal to 4K over L. And this load is known as critical load. At this load, the system will start buckling. So our required load or the applied load, your load that is applied to a system should be less than P critical. So this is the same thing. You can see the restoring moment is K into 2 del theta, and this destabilizing moment which I have discussed in previous slide was P into L by 2 sine of theta. When theta is very small, then it will become P into L by 2 into del theta, and that is known as destabilizing moment. So for safe column or for stable column, we have discussed that this destabilizing moment should be less than the restoring moment. So destabilizing moment is P into L by 2 into del theta, and this restoring moment is equal to K into 2 del theta. So delta theta will be cancelled, and we will have P over here, it will be equal to 4K over L. So your this P is less than 4K over L. And here we have discussed that this P critical is equal to 4K over L. So your P should be less than P critical for safer design. So if your P is greater than P critical, if your applied load is greater than P critical, clear, so the system will be unstable. Now we have the same model that is made up of two rods joined by a torsional spring at C. So if we increase the force P, clear, so initial the theta was delta theta. Now by increasing more load, clear, the angle will be greater, or it will be finite, and it is represented by theta. So assume the load P is applied on the system. So after a small perturbation, the system will settle to a new equilibrium condition that can be seen over here. So the system settled to a new equilibrium configuration at a finite angle. So if you want to analyze it, so we will take this rod AC and we will bring it in equilibrium condition. How you will bring it in equilibrium condition? So definitely if you move this load that is acting at point B to point C, clear, that is P dash. So definitely there will be a reaction movement as well, clear. So that we have already discussed. Now you can see due to this P and P dash there will be a movement, and that movement is equal to P into L by 2 sine of theta. Why? Because this is the force P and the perpendicular distance is this one, and this distance is equal to L by 2 into sine of theta. When you take the sine theta, it will be perpendicular divided by hypotenuse. So perpendicular will be equal to hypotenuse into sine of theta. As the angle is finite, so it will be theta instant of del t. So this movement is known as destabilizing movement. So this is MD. It is destabilizing movement. Clear? And due to the torsional spring at point C, that will tend to restore it. So this movement will be equal to now K into 2 theta. Why? Because the K is the stiffness constant, clear, and the angle which this bar makes with this axis is 2 delta, clear. So in order to find the load, this restoring torque must be equal to this destabilizing. So when you equate them, so this is P into L by 2 sine of theta is equal to K into 2 theta. So this term on the left side is destabilizing moment, and the term on the right side is stabilizing moment. Clear? Now what we will do is that we will divide sine theta on both sides. So you will get, I will write it over here. So you will get P into L by 2 is equal to K into 2 theta over sine theta. Or if you divide it both side by 2K, clear, so that will be equal to P into L over 4K, and that will be equal to theta over sine theta. Now further, if you divide L on in numerator and denominator, so you will get P over 4K over L is equal to theta over sine theta. Now you can see this term 4K over L that we discussed in our previous slide, that is this P critical is equal to 4K over L. Clear? So this is 4K over L. So instead of 4K over L, I can write P over P critical is equal to theta over sine theta. Now when theta is finite or theta is greater, clear? So definitely this sine of theta will be less than equal to theta. So it means that theta is greater and sine of theta is less. So this value on the right side of this equation, clear, it will be greater than 1. So this theta by sine theta will be greater than 1 point something, or it will be greater than 1 point something, like 1 point something, it will be greater than 1. So what does it mean? It means that your applied load is now equal to greater than one value multiply by P critical. So if you have P critical value and you multiply it with a value that is greater than 1, so it means that P is greater than P critical. And when P becomes greater than P critical, so this system will not will not go back to its original position. So it will be destabilized. That is why we say that when P is greater than P critical, so the system is not stable. I hope you have now clear idea. Let's move to another topic, that is famous Euler formula for pin-ended beam. So you can see here that this is a column of length L. This column AB is of length L, and this column is pin supported at both the end. By pin supported mean that here the deflection will be 0 at this pin support. Clear? So this column is acted upon by a load that is P. One more thing that you should understand, that I will explain it, that in beams you have taken the length, the length of the beam in the direction of x. So this was your x-axis and that was your y-axis. So along the length of, or along the axis of the beam, you have taken the length, or whenever you cut the section, so along the length you have taken that distance, while deflection is taken in y direction. Here the same concept is applied. Along the length we will take the distance along the length or along the axis is taken as x. Clear? While deflection, because you can see that due to this load it will buckle, so this is along the length axis. There, this is x-axis, and this is deflection, which is y. So this deflection will be measured in horizontal direction. So you must be able to know along the length of the column you will take the distance x, and the deflection will be measured in horizontal direction. Okay, so this column is pin-ended column, both the ends are pin, so it means that at x is equal to 0, here deflection will be equal to 0. Now here the x will be equal to L, because when you move along the length of direction, so x will become equal to, at this point x will be equal to length, and here y will be also 0. So this is the scenario. Consider an axially loaded beam. So you can see due to this load it will buckle, or it will tend to bend in like a sharp bend. Clear? Clear? And that this phenomena is known as buckling. So in order to find the stability, what we do is that we select a point Q at this end and we cut it and analyze it for further our further analysis. So you can see this is the free body diagram of this column. This is point A. At A there is a load P, and at B there is a load P dash. The boundary condition is also mentioned. At x is equal to 0, y is equal to 0, and at x is equal to L, y is equal to 0. Along the length of the beam, the distance is S, while deflection is shown in horizontal direction, that is Y. Now, when you take this point Q where you want to analyze it and to bring it equilibrium, so this is shown in this figure. So you can see at this point, this force P dash is moved to this point Q. So after moving this point P to Q, so there will be a movement as well, reaction movement will be as well. Clear? Now this as we have taken the section at a distance of x from this point A, clear, and there will be a deflection y. So this is the deflection from this point to this point. This deflection is y. Now when you apply the equilibrium condition, so you can see the sum of moment about point Q is equal to 0. Q is equal to 0. So there is a reaction moment that is again in counterclockwise, so it is positive, and the moment due to this load multiplied by this perpendicular distance, and this perpendicular distance is y. So it will be also positive because it is also counterclockwise. So m plus p into y is equal to 0. It means that this reaction moment is equal to minus p into y. Now this is the moment. Also we know that ei into d square y over dx square is equal to moment. So definitely when you put the value of moment over here, so it will be equal to minus p into y. Clear? So ei into d square y over dx square is equal to minus p into y. If you divide ei on both sides, so you will get equation d square y over dx square is equal to minus py over ei. Okay, so when you further solve this equation, so you can see this d square y over dx square minus, and this will be equal to p into y divided by ei is equal to 0, because you have moved the right side term on the left side, so it will be plus. Now you can see, if we further simplify it, let this term p over ei is equal to another term, and that is known as p square. Let this term become equal to p square. So if you put it in this equation, so you will get d square y over dx square plus p square into y is equal to 0. Now this equation is a differential equation. This equation is a homogeneous differential equation. Homogeneous differential equation of second order. Clear? So this is a homogeneous differential equation of second order. So it's the general solution of this equation will be the general solution of this equation will be equal to y is equal to a into sine of px plus b into cos of px. Now how we will solve this? So definitely you have boundary conditions that at x is equal to 0, y is equal to 0. This was the first boundary condition, and the second boundary condition is that at x is equal to L, y is equal to 0. So in this general solution, you can see A and B are unknown constant which you have to find out. So what we will do is that you have to put this boundary condition in this general solution. So when you put this, the first boundary condition at x is equal to 0, y is equal to 0. So when you will put x will be equal to the sine of 0 is definitely 0, while cos of p into 0, which is 0. So cos of 0 is equal to 1 and y will become 0. I will write at x is equal to 0, y is equal to 0. So y is equal to 0, a into sine of p into 0, which is 0. Clear? And plus b into cos of 0. So cos of 0 is 1, sine of 0 is equal to 0. So this will be cancelled. So b will be equal to 0. So from first boundary condition, we get the value of b, that b is equal to 0. Now for second boundary condition at x is equal to L, y is equal to 0. So you have to put it in this general solution. So y will come 0 and this will be equal to a into sine of p into L plus b into cos of p into L. Clear? As b is equal to 0, so this term will be 0. Clear? And you will get only a into sine of pl is equal to 0. Now what does it mean? It means either a is equal to 0 or sine of pl is equal to 0. Clear? So if a becomes 0, so it means that this a will be 0 and b will be 0, so definitely y will be 0, and this is only possible that when the column become straight and there will be a no deflection. Clear? Or if you want to satisfy this equation, so sine of pl is equal to 0, and when sine of pl becomes 0, because you know that sine of pi is equal to 0, or sine of 2 pi will become equal to 0. So generally if I write sine of n pi is equal to 0. So it means that this become only possible when PL is equal to n into pi. Clear? Now P become equal to L into n pi. So you can put the value of P as well. P square is equal to P, capital P over EI. I will further move to a new slide. Let me clear it. Okay. As we know that this P square was, this P square was equal to P over EI. Clear? And in previous slide we wrote that P into L is equal to n pi. So if you put the value of this small p in this equation, so this will become equal to P over EI under the root, because this is P square is equal to P over EI, this small p will become equal to P over EI. So I have just put the value of P over here into L, and this L is the length of the beam. Okay, this is a capital length, so don't confuse yourself. Okay, is equal to n into pi. So in order to remove this square root, so you have to take the square on both sides. So when you take the square over both sides, it will be equal to PL square over EI, and that will be equal to n square pi square. Further, if you get this P over here, so it will be equal to n square pi square EI divided by L square. So we get the equation of load. So the smallest value of P will be when n is equal to n is equal to 1. So if you put n is equal to 1, so this load will be corresponding to n is equal to 1, and that will be equal to critical load. And this P critical will be equal to pi square EI over L square. And this is the main formula, Euler formula, in order to find the critical load. So this is the P critical, and that is equal to pi square EI over L square. And this applied load should be less than this P critical. Clear? Also, when you put the value of this is the general solution. So from this general solution, you can also get the value of deflection, that this y is equal to a sine of P into L. Clear? So P into L. And this P is again, from here you can see P into L is equal to n pi. So from here P will be equal to n pi over L. When n is equal to 1, so this P will be equal to pi over L. So you can put it in the general solution. So you can also get the value of deflection, that this y will become equal to a sine of pi over L into x. Okay, so let me check it. Here this is x. This distance is x. So you have to put this solution is, this solution was y, because b is equal to 0, so we will get y is equal to a sine of px. So p will become equal to pi over L. So y will become a sine of pi over L into x. So this is the value of deflection. Okay, so this was all about Euler formula for finding the critical load. Again, I will repeat, this formula is only valid for central axial load, and if your applied load is less than P critical, so your column will be stable. So if your P is greater than P critical, so definitely the system will be not stable. So these are the same thing. You can see this was the differential equation, second order homogeneous differential equation with constant coefficient, and from that we get the P critical load. Clear? And the solution will also assume that when P will become greater than P critical, because when P is less than P critical, so we can say that the column will be straight or there will be no deflection. So but when P is greater than P critical, so the solution can be possible. And this P critical is from our previous derivation, that this P critical is equal to pi square EI over L square. Now what if we divide this P critical by the area of the column? So you will get the critical stress. Clear? Again, your applied stress should be less than critical stress. Clear? So this is for safer design. For safer design. If your allowable stress is greater than critical stress, so system will be not stable. So you can see that if you want to find this deflection for the for this system when P is greater than P critical, so you can use this solution. Now P critical is sigma critical or critical stress is equal to P critical over area, and this P critical is equal to pi square EI over A into L square. Clear? If you divide this is the formula. Now we will introduce a new thing that you might have studied, that this second moment of inertia is equal to area into r square, where r is radius of gyration. So if you put the value of I over here, so you will get pi square E A into R square divided by A L square. So A will be cancelled. So you will get, I will write over here, critical stress will be equal to pi square E R square over L square. If you divide this radius of gyration, square of radius of gyration in denominator and numerator, so you will get pi square E over L over R whole square. This is critical stress. Now this L over R is a new term, and which is known as slenderness ratio. Slender, and it is very useful term that will use to check the stability of column. So this sigma critical will become equal to pi square E over L over R whole square, where L over R is known as slenderness ratio, and it is also given over here that this sigma critical is equal to pi square E over L over R whole square. Now we have this critical stress which is equal to pi square E. Instead of I, we have written AR square divided by L square. So if you further simplify it, so you will get the critical stress is pi square E over L over R whole square, where L over R is known as slenderness ratio. Here we have a graph of structural steel, and its modulus of elasticity is 200 gigapascal, and its yield strength is 250 megapascal. So these are the properties of structural steel. So from this, the equation of critical stress, so you can see that this critical stress is directly proportional to this modulus of elasticity, and it is inversely proportional to the slenderness ratio. Means if slenderness ratio is high, so critical stress will be low, and if slenderness ratio is small, so critical stress will be high. So we always try to increase the critical stress, because it is actually strength that define the stability of the structure. So for getting the higher critical stress, you should have lower slenderness ratio. So this graph tells you about the relationship between the L by R slenderness ratio with the normal stress. Now if you look at this graph, so you can see here the L over R is greater and L over R is reducing in the left side. Clear? So when L over R is high, here L over R is high, so you can see the stress corresponding to this L over R is this one. At 200 L over R, so your corresponding stress will be this one. Similarly at 100 it will be like this. Now if you further reduce the slenderness ratio from 100 to 89, so you can see that the stress is increasing. Clear? Or at 89 it is 200, 250, or it is going to increase. I will repeat, when you reduce the slenderness ratio, the critical stress will increase. So at some point, the value of critical stress increases. It means the strength of column is increasing. But on other side, you can see that yield strength of the steel structure is 250 megapascal, and your critical stress is exceeding this yield strength. This horizontal line show you that this is the level of the yield strength for structural steel, and at this value of slenderness ratio you can see the stress is increasing. It means the critical stress or the strength of the structure regarding the stability is increasing, but as it is increasing the yield strength, so definitely the system will not buckle, or system will be stable, but due to this compressive load, the system may yield. Clear? So the system may fail due to the yielding. So this value is of no matter. If you further want to, if you further reduce the slenderness ratio, the strength will increase, but this value will be of no use. So it means that your maximum strength should be the yield strength. Clear? Because you have to also check whether it is not increasing or exceeding the material property. So here I will repeat that the critical strength is increasing, but on other hand, you are going to the higher side of the stress that will exceed the yield strength, and the material or the column will fail due to the compression yielding, compressive load, and it will yield. So this critical stress should be enhanced, but it should not exceed the material property or yield strength of the material. Now we will move toward another topic, that is extension of Euler formula. So in our previous slide we discussed the Euler formula for the column whose both ends were pinned. Now we will apply our knowledge to the column whose one end is fixed. You can see one end is fixed and other end is free. So that is extension of Euler formula to the other type of the columns. So you can see this is a column whose one end is fixed while other end is free. When you applied the load, it will buckle. Now it's when it buckles, you can see that this buckling is similar to the half of the, this is showing the same behavior as here, the half. Clear? So again, if you extend it, clear? So if you extend it like this, so this is total length is L, so this total length will be now equal to 2L, and this length will be equal to effective length. Now this column shows the behavior of column having both end pinned, and for both end pinned we have critical stress is equal to pi square EI over L square. Now when the column is whose one end is fixed and other end is free, so here this length will become equal to 2L, and it will be known as effective length. So this P critical will be equal to, the same formula will be used, but here instead of L, this L will be equal to L effective, where L effective will be equal to 2 times of L. So while solving problem, you have to be careful and you have to choose effective length is equal to L while you deal with the problem or column having one end fixed and other end is free. Rest all the things are same. So P critical is equal to pi square EI over LE square, and critical stress will be equal to pi square E over LE over R square. Instead of L, you have now to write LE over R square, and this effective length is equal to 2L. Okay, up till now we discussed the column whose both ends are pinned. So in that case, effective length is equal to L, that we discussed earlier. After that, we discussed the column with one fixed end and other end free. So in that condition, the effective length LE is equal to 2L. Now we will extend toward another type of column, that is one end is fixed and other end is pinned. So you can see its one end is fixed while at this point A it is pinned. So in such type of column, this effective length LE is equal to 0.7L. The fourth type of column is that one whose both ends are fixed. So you can see this end of the column is fixed and this end is the fixed. So in that scenario, the effective length is LE is equal to 0.5L. All these are available in the table of the book, that is Mechanics of Material by Baer and Johnston. So their derivations are also available. We will not go into the derivations. We will just pick that if you have the beam like this, so effective length will be equal to this one. If both ends are pinned, so you will use LE is equal to L, and if one end is fixed and other end is pinned, so LE will be equal to 0.7 L. And if both ends are fixed, so LE will be equal to 0.5 L. And the rest you can put it in the Euler formula in order to get your desired critical stress and critical load and critical stress. We will solve some certain problems so that you have clear idea about that. So let's move further. Okay, so this is the problem. The statement of problem is that a 2 meter long pin-ended column. So you can see both ends are pin-ended. Clear? At point C and at point D, the both ends are pinned, and the length of column is 2 meter with a square cross section is to be made up of wood. So this column is of square cross section and it is made up of wood. Also, E is given, modulus of elasticity, that is 13 gigapascal, and allowable stress is 12 megapascal, and factor of safety is 2.5. So what we have to ask is that calculate Euler critical load for buckling and determine the size of cross section if the column is to safely support a load of 100 kilonewton and 200 kilonewton. So let's start with the solution. As you have the data available over here, so you can see you have the factor of safety, you have the allowable stress, and the load is given. Clear? Modulus of elasticity is given. So for first part, for a load of P is equal to 100 kilonewton. Also, we know that critical stress load is equal to pi square EI over L square. You know that. Why I am writing this? Because you have to determine the cross sectional of the column. You have to calculate the critical load for buckling and determine the size of column. So you know that critical load is equal to pi square EI over L square. So you have E value. You do not have I because you do not know the cross sectional area. Clear? You have the length. So first we will find the critical load. So factor of safety is also given, that is 2.5, and you know that factor of safety is equal to critical load divided by the applied load. So you can see your applied load will be equal to P critical over factor of safety. P critical is given as P critical is not given, only load is given. So what we have to find the P critical. So P critical will be equal to factor of safety multiplied by this load P. So 2.5 multiplied by the given load is 100. So when you multiply it, it will be equal to 250 kilonewton. Clear? So your load, applied load is 100 and your critical load is due to factor of safety of 2.5. Your critical load is 250 kilonewton. So you have now critical P critical and you have pi value, E value, L value. So you can calculate I, and this I will be equal to P critical multiplied by L square divided by E pi square into E. So you can put the value P critical is 250 kilonewton, so 10 raised to power 3, and length is 2 meters, so it will be 2 square, clear, divided by pi square into E is 13 gigapascal, so 13 into 10 raised to power 9 Pascal. So when you calculate it, it will be 7.794 into 10 raised to power minus 6 meter 4. So this is the value of moment of inertia. Now we have been given that this is a square shape. square in cross sectional area. So let, if this side is A, so definitely this side will also A. Clear? And I for square section, that is equal to 1 over 12 BH cube, and B is A and H is also A, so it will be equal to 1 over 12 A4. Okay, so from here you can calculate its dimensions. So A4 will be equal to 12 times I. Now put the value of I12 into 7.794 into 10 raised to the power minus 6, and when by using scientific calculator you can find A, and this A will be equal to 98.3 millimeter, or you can say it will become odd 98.3, so you can say that A is approximately equal to 100 millimeter. So this is the load, this is the cross sectional 100 by 100 millimeter by 100 millimeter cross sectional area, 100 millimeter by 100 millimeter square cross section is selected for the load of P 100 kilonewton that will not buckle, because you can see that your critical load is 250 megapascal, clear, 250 kilonewton, and your applied load is 100 kilonewton. Now you have the cross-sectional area, you can also find the critical stress. So critical stress is equal to critical load over the area. Not critical stress. You can also find the stress due to this load P. So this load P, stress is equal to P divided by A. So you have P, which is 100 kilonewton. So 100 into 10 raised to the power 3 divided by area is A square, and this A square will be equal to 0.100 square, because this is in millimeter and you have to convert into meter. So this stress will be equal to 10 megapascal. Now you can see, due to this load, the stress is 10 megapascal and your allowable stress is 12 megapascal. So your applied stress is less than allowable stress, so it means the design will be safe. And also P critical, that is 250 kilonewton, that is greater than P, clear? So it will not buckle at this load, at load of 100 kilonewton. Now in second part you have 200 kilonewton. So again you will use the same concept. You have P is equal to now 200 kilonewton. So again, by using formula, P is equal to factor of safety into P is equal to P critical. So from here factor of safety is 2.5 and P critical, P is 200 kilonewton. So you can calculate P critical, and that P critical is equal to 500 kilonewton. So when you put P critical in this, I is equal to P critical L square over pi square E. So when you put all the values, so you will get this I will be equal to 15.58 into 10 raised to the power minus 6 meter 4. And from this, we have been asked to find the cross-sectional area of square for this load. So I is 1 over 12 A4 is equal to I, which is equal to 15.58 into 10 raised to the power minus 6 meter 4. So you can get the value of A from this, and that will be equal to 116.95. Okay, 95 millimeter. So a cross section of, you can say, A is equal to 117 millimeter. So the area cross section, this is 117 millimeter and this is 117 millimeter. Now we will check the stress, normal stress, and normal stress is equal to load by area. The load is 200, so 200 into 10 raised to power 3 divided by area is 0.117 whole square, because this is square in cross section. So when you calculate it, this stress is 116. When you calculate it, this value is 14.62. This value is 14.62 megapascal. Okay, now you can see due to a load of 200 kilonewton that is applied on a square cross section of 117 by 117, the stress is 14.62. But in question it is given that allowable stress is 12 megapascal. Clear? So here you can see this stress is greater than allowable stress. Clear? And that is larger. So dimension obtained is, so this cross sectional area is not acceptable for this load, for P is equal to 200 kilonewton with a factor of safety of 2.5. So what will you do? What will you do is that you can find out the cross sectional area by using allowable stress. So allowable stress is equal to P divided by A. Clear? So you can have A is equal to P divided by sigma allowable. P is 200 because we are going to find out the cross sectional area for this load, and allowable stress is 12 megapascal. So 12 into 10 raised to power 6 pascal. So from here you can get area is equal to 16.67 into 10 raised to power minus 3 square meter. Now since we have to choose the dimensions of square, so it will be equal to, area will be equal to A square. So A square is equal to 16.67 into 10 raised to power minus 3. And when you solve it using calculator, so you will have A is equal to 129.1 millimeter. So a square cross section of dimensions 129.1 millimeter multiplied by 129.1 millimeter is acceptable for the load of P is equal to 200 and allowable stress is equal to 12 megapascal. I hope it is clear to you now. Okay, next is sample problem 10.1. So the statement is that an aluminium column of length L and a rectangular cross section has fixed end at B and support a centric load at A. So you can see this is a column of rectangular cross sectional area at B and it is fixed, while at end A there is a centric axial load P applied on that. Two smooth and rounded fixed plate restrain end A from moving it on one of the vertical planes of the symmetry, but allow it to move in the other plane. So you can see there are the two round-ended plates that restrain the movement in this plane. This X, this is the X-axis, this is Y-axis, this is Z-axis, and along the load, this is X-axis. So it restrained the movement of this column in XY plane. So you cannot move it in the Y direction, but it can move in the XZ plane. So this is XZ plane, so it can move in the XZ plane. What we have asked that determine the ratio of A/B. So you have to determine the ratio between A is the thickness and B is the width of the two sides of the cross section corresponding to most efficient design against buckling, and B part is design most efficient cross section for the column. some data about length is given. Length is 20 inch. Modulus of elasticity is given 10.1 into 10 to the power 6 psi. Load is given 5 kips and F factor of safety is 2.5. That is given. So before starting before solving this problem, let me discuss that when you applied the force or load on this column, centric load on this column, the column may buckle in xz direction, it may buckle over here, it may buckle over here, or it may buckle in xy plane. It may buckle like this as well. It may buckle like this as well. Clear? In xy plane. Either it will buckle in xy or it will buckle in the xz plane, in this direction, in this side or this side. So how you will know that in which plane it will buckle? So always remember that it will buckle, buckling will occur, buckling in plane will occur whose moment of inertia in that plane is less. Clear? So this is the criteria. So you have to check the moment of inertia about y-axis as well as z-axis. So if moment of inertia about x-axis is less, so it will buckle like this, and if moment of inertia about z-axis is less, so it will buckle in xz plane. Clear? So let's move toward the solution. We have been asked to determine the ratio AB of the two-sided cross section corresponding to most efficient design in the buckling. So most efficient design of the buckling will only possible when the slenderness ratio in xz plane will be equal to slenderness ratio in the xy plane. So we will use this criteria and we will solve this problem. So the most efficient design occur when the resistance to buckling is equal to in both plane of the symmetry. So when the resistance of buckling is equal, when the L over R ratio in xy plane is equal to L over R ratio in xz plane. So this is the x-axis. This is y-axis and this is z-axis. So we will start finding L over R ratio for xy plane first. Then we will find L over R ratio for xz plane, and then we will equate it. So let's move. So you can see our focus is buckling in xy plane. So you will have to concentrate in xy plane. Okay, so L is same for both, and R you have to find radius of gyration, and you know that radius of I about buckling in xy plane. Buckling in xy plane means the rotation or moment of inertia about z-axis. Clear? Xy plane, so I will be Iz. So Iz is equal to area into Rz, radius of gyration square. Clear? So this R square will be equal to Iz over A. Now you can see this is x, this is y, this is x, and this is moment of inertia about z axis. So you can see this will be your this is your height. Clear? And this is your breadth. Clear? Okay. Also you can see if you draw the cross-sectional area like this, and this is your z-axis. This is your z-axis. So you can see this distance is A, and this distance is equal to B. So moment of inertia is equal to 1 over 2 B into H cube. So B here B is this, and height is A. So it is equal to 1 over 12 B into A cube, and area is equal to area of this cross sectional is A into B. So when you put the value, so you will get A square over 12. RZ radius of gyration will be equal to A over under root 12. Clear? Now we will find the L over RZ ratio LEZ over R ratio. And here the length will be used as effective length. So we will check for effective length as well as. Now you can see that in XY plane, it is restrained. Clear? You cannot move it in the XY plane. Clear? This column cannot move in XY plane. So definitely this acts like a behavior of this beam. One end fixed and other end is pinned. So effective length is 0.7 L. I will explain it further. You can see I have already told you that this column cannot move in XY plane. This is Y, this is X, so it cannot move in XY plane. So it means that this end is like pin end and other end is fixed. So for the column that one end is pin and other end is fixed, the effective length is 0.7 L. And the radius of gyration is already A over under root 12. So this is LE in Z, about Z over RZ is equal to this value. Now we will move toward the buckling in XZ plane. So for that we will also find LEY, because in XZ plane and you have to find the moment of inertia about y-axis. Clear? So in y-axis you have to find the moment of inertia. So your LEY divided by RY, that you have to find. Clear? So first we will find RY, radius of gyration in about y-axis. So again this radius of gyration about y-axis is equal to ry square is equal to iy over a. Now you can see if you draw it like this, and this is y-axis. Clear? This is y-axis. This was a, this is the a, and this is b. So iy is equal to 1 over 12. B is over, now here is A, breadth is A. So A and height is B. So 1 over 12 breadth into height cube, and that is 1 over 12 AB cube divided by area is AB. So when you solve this, so you will get radius of gyration is equal to B over under root 12. Clear? Now we will check for effective length. So you can see that this beam can move in XZ direction, XZ plane. Clear? So it can move in this plane, XZ plane. Clear? So it means that this end is free while B end is fixed. So it will be a column whose one end is column with one end free and other end is fixed. So we have already discussed that in such case, if one end is free and other end is fixed, so the effective length is equal to 2L. So you can see LEY is equal to 2L divided by radius of gyration about y-axis. So you have both the values, so you can put it, you will get 2L over B over under root 12. Now for most efficient design, this LEZ over RZ should be equal to LEY over RY. So if you equate this value with this, so you can see it is already written over here. So this is equal to this term and this is equal to this term. So you can get the ratio of A by B, which is equal to 0.35. So this is already given that you have to find the ratio of AB of two sided of the cross section to correspond the efficient design. So the ratio of both sides A over B is 0.35. Next is to find the most efficient cross section of the column. So we will move toward the second part. Now as we discussed that L over R ratio in both the planes should be equal, so you can take any one. So here we have taken LEY over RY, and its value is already 2L over B over under root 12. Now L is given, B is not available, clear? So you can calculate it. LE over RY. RY is radius of gyration about y-axis, that is equal to 138.6 divided by B. Also factor of safety is given. You can see factor of safety is given, load is given, so you can find critical load, and this critical load will be equal to factor of safety into load P. So when you multiply this 5 with 2.5, so you will get critical load is 12.5, and critical stress is equal to critical load over area. Now critical load is 12.5 kips, so you have to convert it into pounds. So 12.5 into 10 raised to power 3 pounds divided by area. Now area, since this is rectangular whose breadth is B and one side is A, clear? And it is also find from our previous ratio that A by B is equal to 0.35, clear? So A will be equal to 0.35 times B, clear? And area of rectangle A is equal to A into B, clear? And since A is equal to 0.35 B and this B, so area will be equal to 0.35 B square. So this is the area, or when you put it over here and you will calculate it, this will be your critical stress, clear? Also we know that critical stress sigma R is equal, sigma CR is equal to pi square E over LE over R whole square. So for that this length is 20 inch, clear? Okay, LE over R square. Okay. Now, okay, so LE over R for this about y-axis are in xz plane is already 138.6 divided by B. So critical, we know that pi value is pi square E is given 10.1 into 10 raised to power 6, and L over ER is 138.6 divided by B whole square. So one equation of critical stress is this, and one equation of critical stress is this. Now you can equate this value with this one that is given over here. There. So when you equate it, you will get the value of B, which is equal to 1.620 inch. Now you have the value of B, you can put B over here and multiply it with 0.35, so you will get 0.567. So this is the rectangular cross-sectional area of the column with B is equal to 1.620 and A is equal to 0.567. And that was all about Euler formula for different type of column with the end condition, with different end condition. And one more thing, that all that we have done is only limited to centric axial loading. In our next lecture we will discuss eccentric loaded, that when load is not applied at the center or not passing through the central axis, clear? Instead of that, it will offset at certain distance E, that is known as eccentric load. That is we will discuss inshallah in our next lecture. That will be the part 2 of this chapter number 10 in our upcoming lecture. I hope you have enjoyed my video, and if you haven't subscribed my channel, kindly subscribe it and keep on learning more and more. Thank you for watching.